Okay, let's just dive right into this. I mean, we hear the buzzword deep learning absolutely everywhere these days, right? It's in our news feeds, our tech blogs, and literally every corporate keynote. But what does it actually mean? Today, in this explainer, we're going to cut through all that hype and look at the actual practical mechanics of how this stuff works. You kind of have to wonder, is deep just some slick marketing trick cooked up to sell more software? Or is there a tangible mechanical reality to it? Well, it turns out there is a very literal architectural reason for that word, and understanding it is absolutely crucial to unlocking how all modern AI functions.
Section 1. What is deep learning?
Before we get into all the complex applications running our world, let's ground ourselves for a second. Deep learning isn't just a blanket term for all AI. Not at all. It's actually a highly specific subfield of machine learning that uses multi-layered neural networks for some very targeted tasks. Tasks like classification, figuring out if a photo is a cat or a dog, or regression, which predicts continuous outcomes like tomorrow's stock price. It even handles what's called representation learning, where the system acts almost like a detective, discovering the complex features it needs to categorize data entirely on its own.
Section 2. Stacking the artificial layers.
So, taking heavy inspiration from biological brains, scientists figured out a mechanical way to process all this data, and it really revolves around 3 structured steps. First, you take artificial neurons, which honestly are essentially just math functions, and you stack them. Step 2, you form these structures into multiple distinct layers. And finally, step 3, you train the network. You can hold its hand with labeled examples in supervised learning, or just set it loose to find hidden patterns entirely on its own, using unsupervised methods.
And this brilliantly answers our initial question. The adjective deep literally refers to the number of layers. A simple traditional neural network might have just one hidden layer, but deep learning, it uses anywhere from 3 to several hundreds to even thousands of layers stacked on top of each other. That sheer, massive depth is exactly what gives it its mathematical superpower.
Section 3. Types of network architectures.
Now, you don't just stack thousands of layers randomly. They are engineered into highly specific architectures designed for completely different jobs. We aren't just using one generic model here. For example, recurrent neural networks, or RNNs, they're your go-to for sequential data, like audio. Convolutional neural networks, CNNs, they completely revolutionize how computers see images. And then we have transformers. Those are the engines behind modern text AI, like the chatbots we use every single day. Each one represents a radically different way of wiring those thousands of layers together.
Section 4. Real-world AI applications. But look, complex architectures only really matter when they solve actual human problems, right? And these systems are practically running the modern world. In medicine, they aren't just analyzing images, they are revolutionizing drug design by predicting how proteins fold, like we've seen with AlphaFold. Over in audio and language, they are the seamless translation tools breaking down barriers in real time. And in strategy, they've gone from playing simple games to mastering impossibly complex programs like Go, literally outsmarting human champions.
The reaction across all these industries has been, frankly, seismic. And here's the core reason why. In highly technical fields, these models aren't just matching human experts anymore. They are producing results that actively surpass human performance. When a machine can flag a microscopic defect in a jet engine part or spot an anomaly in an X-ray faster and more accurately than a trained human professional, that fundamentally shifts how our world operates.
Section 5. Not a human brain.
Now, it's incredibly easy to look at those superhuman results and jump to some wild sci-fi conclusions. But before we assume we've just built a literal, mechanical human brain in a server rack somewhere, we need a serious reality check. While early forms of AI were absolutely inspired by biological neurons, the current reality has completely diverged. Modern neural networks do not even try to model actual brain function. They have evolved into distinct, bizarrely alien mathematical frameworks that process data in ways our biology simply doesn't.
In fact, researchers emphasize a pretty fascinating irony about this divide. If a neuroscientist actually tried to use today's advanced AI to understand true biological brain function, well, it's generally seen as a remarkably low-quality model for that job. They are mathematical powerhouses, for sure, but they make terrible biological replicas.
So, the big takeaway for you from this explainer is this. Deep learning is a highly structured, multi-layered mathematical tool that has totally outgrown its biological inspiration. It isn't a synthetic human brain at all. And honestly, realizing that actually makes it even more exciting. Because if this technology isn't just trying to be a mechanical replica of us,
What entirely new, non-biological forms of intelligence is it going to unlock next?